There's an energy equation for a particle in a central field, and we can just write it as the kinetic energy plus the potential energy equals the total energy. And so this is just 1/2 mv squared plus the potential energy equals E. The potential energy depends on the kind of force it is. It could be, a kqq over r squared, gmm over kqq over r, gmm over r negative, or anything else. We're just saying it's a central field. It's not necessarily 1 over r squared. And so we're going to try to write down a differential equation for this. The E is just a constant, right? That's the total energy, and that's the kinetic plus the potential. And so if we do this in polar coordinates, we know that r is equal to r e hat r, like that. And we've done this before, right? The velocity is equal to r dot, which is equal to r dot e hat r plus r theta dot e hat theta. And so this is the polar coordinates version of this. And so if we want to calculate v squared for 1/2 mv squared, we can just take v dot v, like that. Dot product that with itself, e hat r and e hat theta are perpendicular, and so this is just the square of the individual terms, which is r dot squared plus r squared theta dot squared. And then we can sort of start to break this down the way we did when we were solving differential equations. And one of the things we did was we said, well, r is equal to 1 over u, and so r dot is equal to minus 1 over u squared du dt, and that was minus 1 over u squared du d theta dt, which is just theta dot, and so that was minus 1 over r squared theta dot du d theta, right? Similarly, theta dot was equal to the angular momentum per unit mass times u squared. It came from r squared theta was equal to the angular momentum per unit. R squared theta dot was equal to the angular momentum per unit mass. Divide by r squared and you get this guy. And so if we start making some substitutions, like if we substitute this guy into that guy, we get, dang it, I'm going to start over. So we're going to talk about the energy of a particle in a central field. This isn't necessarily 1 over r squared. We're going to look at this in polar coordinates. I'm going to draw back on some of the things we did in chapter 1 and in the beginning, mostly in the beginning of this chapter. And we're going to say, look, the kinetic energy plus the potential energy is equal to a constant, which we'll call E, the total energy. And all this is what you're familiar with. This is 1/2 mv squared plus the potential energy is equal to some constant. Now this guy could be negative gmm over r, but it could also be any other thing. It just depends on whatever the potential energy is being supplied. All that matters is it comes from a point. It's radial. And so so we're going to turn this all into sort of like a differential equation, but we're going to start by writing this guy in polar coordinates. And so v squared is just v dot v, right? And v is equal to r dot, which is dr dt, and that's equal to the time derivative of r e hat r, right? And we've done this already. That's equal to r dot e hat r plus r theta dot e hat theta. And that's my velocity. And so v squared is just the dot product of this thing with itself. Since e hat r and e hat theta are perpendicular, I get r dot squared plus r squared theta dot squared. And so we have to do a few things to work this out. First, as in the beginning of the chapter, we made this substitution. We said r is equal to 1 over u, and so dr dt is equal to minus 1 over u squared du dt, which is minus 1 over u squared du d theta dt. And so r dot, that's what this is minus 1 over u squared theta dot du d theta. So that gets us this part of it if we square it, right? But we have some other work to do. Also in the beginning of the chapter, when we were looking at Kepler's second law, we found that r squared theta dot is equal to the angular momentum per unit mass, and that's a constant of motion. And so that means that theta dot is equal to L over r squared, or is equal to u squared L. And so I can substitute in here, for example, I can say r dot is equal to minus 1 over u squared times theta dot, which is u squared L, and that's du d theta. And so this is, let me see if I get it right, minus L du d theta, and that's r dot. And so I can substitute that in here. I can come back and I can say, look, v squared is equal to this quantity squared, so it's L squared times du d theta squared. And now I want to look at this guy, right? And I'm going to say, well, r squared theta dot squared is equal to r squared times this quantity squared, u squared L squared. And that's equal to 1 over u squared times u to the 4th L squared, which is equal to u squared L squared. And so the whole v squared becomes this piece plus u squared L squared, right? And so this is the piece we can then stick in here to write our energy equation. And so I'll do that on the next sheet. So I've rewritten this. Here's my conservation of energy equation: kinetic plus potential energy equals E. And all I've just done is replace the v squared with the v squared I had on the previous page, and that looks like this. And I'm going to factor out an L squared out of the parentheses, and so I'm going to have 1/2 m L squared times du d theta squared plus u squared plus v. I can write it v of r, I can write it as v of u, it doesn't matter. It depends on both of them. Equals E. Right, and so that's my conservation of energy equation. So for one over r squared forces, or for k over r squared forces, like gmm over r squared and so on, the potential energy can be written this way: minus k over r, or just minus ku. And then we can move that to the other side, and we get and sort of divide out this factor, and we get d squared u. Sorry, not d squared u. We have to be careful on that. Du d theta squared plus u squared is equal to 2 over m L squared times E minus ku. Sorry, plus ku. And then I can subtract a u squared over there, and I can say, look, du d theta is equal to 2ml squared, 2 over ml squared times E minus KU minus U squared. And then I can separate variables, and I can say, I don't know if I have room over here, but I'll just try to write it up here. Du over all of this, 2 over ml squared times E minus KU minus U squared is equal to d theta. And now I've separated variables. This side all depends on U, and this side all depends on theta, and we'll look at that on the next screen. So we separate variables here, and then we can write it this way. This is just a generic form of this. We've rearranged it slightly where we've chosen A, B, and C to have these values. And then you can just do a table lookup on this integral, and it ends up being a cosine function with these coefficients once you've resubstituted. And then you can solve for r in terms of theta, and this starts to look very much like the things we've talked about already. This was the latus rectum alpha, and this square root here, the coefficient for the cosine term, is the eccentricity. And so we'll write that on the next screen, but you can see already that when this coefficient is less than 1, in other words, when E is less than 0, we get an ellipse, or we get a closed orbit, ellipse or a circle, or something like that. And so total energy less than 0 is a closed orbit, and that's what we were talking about earlier. It's kind of trapped. Its energy isn't high enough to escape. If E is equal to 0, then it's a parabolic orbit, and that's just enough to get it away. And finally, if E is greater than 0, the orbit is then hyperbolic, and the orbiting object gets to infinity and still has energy left over. Okay, as far as the energy is concerned, that's the energy equation is concerned. That's the equation for the eccentricity. And so there's the energy. The K is, GMM or whatever it is. And so we can do an example. This is 6.10.1, but really it's just an example. It says a comet has speed v and distance r from the sun, and the speed and r are at an angle phi. In other words, so if I have an orbit here, right, here's the sun, that's r, and that's v, and the angle between them, which I guess is this angle, would be phi, right? And so the question is, determine the eccentricity E of the orbit. Right, and so here's my formula for E, and so I can really just plug into that. K is equal to G M M, right? L is equal to the magnitude of R cross V, which is equal to RV sine phi. And so L squared is equal to R squared V squared sine squared phi. And so you can just plug into those things, right? And you get I'm going to substitute in for E here. So I'm going to say E is equal to 1/2 m v squared minus g m over r. Right, so this is all written again in terms of my v and my r. And so instead of having 2e, I'm going to have 2 times 1/2 mv squared minus g m over r. And that's over g m, right? And then I have m l squared, and the l squared I'm going to replace with r squared v squared sine squared phi, right? And that's also over GMM. And so if you look at this problem, all the m's cancel, those m's cancel, and those m's cancel. Not the big m's, but all the little m's cancel. And so if I know v and r and phi, v and r and phi, that's all I have here except for like the mass of the sun. And so I can evaluate E is just this, and if I plug in an r and a v and a phi, I can evaluate that eccentricity.